Okay, good morning. Just say the title, so I don't repeat that. My quotes are Francisco Rey from the Institute. I'm a bit sorry, but it's not your friend, so another friend. Call him Pancho. So you could not put it into your CV, friend. And we have John Egil Skjæråsen and Christian Jørgens from the University of Bergen. Okay, in this talk I will focus on the Northeast Arctic Code, and then I will give some background, switch to materials and methods, and then go into simulation in a warming situation, say some words about size-specific spawning time, and then to match-mismatch theory, that is overlap between the zooplankton and the cod larvae in time, and then I switch to conclusions. Okay, background. This is the code we are working on, Northeast Arctic Code. Okay, as you all know, that there's a predicted temperature increase based on the work that IPCC has undertaken, and this is from their 4th assessment report, and the 5th assessment report just coming soon is saying very much the same. And as you see here, this is a very sensitive. You see that the highest temperature is coming in the north. Okay, and then we switch to the code. And this is based on a publication about drink water, and that is assumed temperature increase in the water that is inhabited by the code. So if you switch to our code then, the Northeast Arctic Code, he is saying that the temperature is increasing from 3 to 6 degrees, but that depends on many factors, but they are quite sure that there will be a temperature increase. Okay, this is the area where the Northeast Arctic cod is living. It's feeding in the Barents Sea and migrate down to Lofoten, Vesterålen to spawn every year. So we will be focusing very much on this Lofoten area in this talk. So I just present first a little bit the way we are thinking. And we are starting down here on basic physiology, adult cod physiology. And then we are adding in temperature and day length, and then we get the expression of the reproduction, and adding in body size, and get an expression of the spawning time. But in this presentation, I will not say anything about body condition. We are assuming that this fish is in normal condition. And then we move up to match-mismatch, adding phytoplankton and zooplankton to see if there's an overlap between the cod larvae and the zooplankton peak. At least I know much more in this area than in this area, so I call this the area of greater uncertainty. But the second author of this paper has worked on in this area here, especially on phytoplankton, for 30 years. So that's a good thing. So why are we working on this? And the reason is that if you look at this figure to the right there, made by Portner et al., Portner and Farrell, you see that the thermal window is much smaller for eggs and spawners, while the growing adults and juveniles, they are much more robust to temperature change. So the critical periods are the eggs, larvae, and the spawners. Okay, materials and methods. I will not go in details through this list. It's a long list, and actually you can spend the whole life working on this formula that is behind there, but we have done our best. So many things that are in bold here is that what I will show you a little bit later. So spawning time, we use this paper. Spawning period, we use this paper and unpublished data. Phytoplankton spring bloom. We use open sources, the Ocean Weather Station Mike in Norwegian Sea to estimate this extinction coefficient, and also a paper by the second author. hatching of colonies eggs, we consulted LH et al., developed type of copepodite 1. We used so-called Belle-Radek function, zooplankton peak. We assumed a linear increase in temperature, switch from nuclei to copepodites, a mortality function, code egg development, Geffen et al., code larval first feeding, Otterley et al., code critical first feeding window, Knudsen and Tilset, code larval survival, proportional to code food availability, and code adult growth model, Enberg et al. Okay, first I will show you a little bit a schematic. This is a schematic thing, and we are assuming a fish of a given size. And how spawning time is influenced by light cycle, temperature, and fish condition. Okay, so if you look here on this panel, you see here we have the time on the x-axis here, and on the y-axis we have an expression of the maturity stage, and what we are using as maturity stage is the leading quart oocyte size, the 10% biggest oocytes in the ovary. Okay, and the maximum, when the fish reach this area here, the fish starts to spawn. Okay, and we say that the fish start to mature when the nights get longer than the days, and that is happening in the autumn after equinox. So that is the starting, that's the trigger. We assume that the oocyte growth rate is linear, and that is based on experimental study. The other also based on experimental studies. And the blue here is referring to a cold year, and you see that this fish will start spawning in April. You see crossing the line here, and then it will be spawning here in April. Okay, and when it gets warmer, this slope will get steeper, and you see here in this one, warm water will spawn here in around January. Okay, but here we ignore the condition effect, but if the fish is in a little bit poor condition, the spawning time will be delayed, typically about a couple of weeks. But it's even more in poor condition, it will skip spawning. But here we are not talking about the condition effect. Okay. In addition to this, this effect, we have also an effect of body size that we also had to include, and that is again based on experimental studies. And we are, as in the previous, we are assuming that when the temperature gets warmer, the fish is spawning earlier. But at one temperature, the size effect starts to kick in, and we believe that is around 5 degrees Celsius, and we believe that the bigger fish will be spawning first, and that is confirmed by looking at fish in the Irish Sea and the North Sea, and also comparing with the Barents Sea code. So we are quite reasonable sure that this is correct. Okay, and then we go into how to estimate the time to copepodite 1, and we consulted these publications here, and here you have temperature, and here you have the time, and so you see that this is a very nice relationship, and this refers to the whole North Atlantic. So this is a very strong relationship. Okay. Then I will be showing 3 panels from the Lofoten area in a warm year, normal year, and a cold year. And this blue line here is the temperature. You see them here? And the green here is the phytoplankton peak, and that is modeled. And you can see that it's quite similar in those 3 years, and that is because there is many other factors than temperature that is influencing when the phytoplankton peak is appearing. One is light, and the other is the depth of the upper mixed layer. And here you have the zooplankton peak, but here you see that the zooplankton peak appears later when the water gets colder, and you also see that the shape of the zooplankton peak is changing. So in the cold year, you have a tail here to the left. The nice thing with this is that it is actually matched what they see in the field, and that is based on our work by DL and Tande, a little bit further north of Tromsø, Lofoten. Okay, a little bit about the simulations. Here it is important to notice that we are speaking about three temperatures. One temperature is during the maturation cycle, the genesis, and that is when the cod is in the Barents Sea, okay? And that temperature we are setting to be varying depending on its climate change effects. And the other temperature is during spawning in the thermocline, and we are saying that that is fixed. That is not there. The cod is selecting this temperature. And then it's the temperature of the plankton, cod eggs, and the larvae in the upper mixed layer, and we are saying that that is also varying. Typically, the temperature in the upper mixed layer is 1 to 2 degrees lower than the vitogenic temperature. Okay, so why are we setting that the temperature of the spawning is fixed? And then we have, based on observation in the Lofoten area, when the cod is spawning between 4 to 6 degrees Celsius, but also this very nice work of Wright et al. And here you see this is based on data storage text information, and you see this is the temperature that the cod in the North Atlantic is visiting. But this is the temperature during the broken line, is during spawning. And one interesting thing here is that they are not spawning above 10 degrees Celsius. And 5 to 7 degrees Celsius is a typical temperature, but in the Lofoten area, it's more typical 4 to 6, and therefore we selected 5. Okay, this is an illustration to show what we are talking about. So this is on the cod spawning. So this is the time of the year. So here the cod is starting to spawn, and then this is when it is spawning. And you see that the time of spawning and when it actually spawning is a bit, the last is a bit broader, and that is because the cod is spawning different number of batches, so this will be broader. And here is when the first feeding larvae appear. Okay, this one is in a warm situation, and this is the first feeding larvae. And we are saying that they appear later in the small fish and progressively earlier in the bigger fish. And we just inserted these zooplankton peaks just to show you an example. So this is the things that we are working on. Okay, some of the results here. And here is the appearance of the cod first feeding larvae in relation to the length of the fish, mother fish. And as I say, at 5 degrees Celsius, you don't have a fish size effect, but that starts to kick in at 7 or even higher at 9 degrees Celsius. And this 3 panels here is showing the overlap with the zooplankton. And in 5 degrees Celsius, we didn't find very much overlap. But at 7 degrees Celsius, we see that the bigger fish has an overlap with the zooplankton, or the offspring of the bigger fish. At even higher temperature is the medium-sized fish that shows this overlap. Okay. Overlap, match-mismatch, and the effect of fishing. So blue here is no overlap, and this brownish here is full overlap. And here your temperature, this is the vitogenic temperature during maturation. And here is the age of the fish. And actually the cod can be up to 25 years results, but today they are not 25, they are maybe 10 to 12, 13. But in a model, we can do that, okay? And you see here that the biggest overlap is happening when the temperature in the Barents Sea system is 7-8 degrees Celsius, so a little bit higher than today. So we are expecting that the overlap will be actually increasing with the temperature increase. Here we have included fishing, and it's basically the same story, otherwise, except that it's the truncated age distribution. Okay, so my conclusion then, we assume that cod spawning time is a function of temperature and body size based on experimental and field data. Present status of knowledge about phytoplankton bloom in the coastal waters was included in the model. A complex model was established to locate the timing of the zooplankton peak and first feeding Northeast Arctic cod larvae in a warm, normal, and cold year in coastal waters. Please notice that we are talking about coastal water and oceanic waters. It's different. In warmer waters, the larvae from larger cod showed a better overlap than those from smaller cod, while medium-sized cod had the best overlap in very warm waters. The main effect of fishing was to truncate the age distribution. The degree of match-mismatch was quite similar as without fishing. And then I show you a picture from Lofoten.